In this presentation, we're going to take a look at methionine scarcity and lactating diets and what the implications of that scarcity are for efficient use of lysine for milk protein synthesis. And we're going to approach this by looking at some very critical fundamental concepts that often get lost in our efforts to balance for amino acids, but they're critical and we need to bear them in mind and focus our attempt to balance for increased milk protein yield in these three areas. So let's take a look at this. There are three underlying predicates that are absolutely essential as we approach the idea of balancing a diet for amino acid content to improve protein yield. The first of those predicates is that amino acids are the building blocks for tissue and milk proteins, but they're not random building blocks that somehow just happen to fall into place. They're joined together in proteins according to a predetermined genetic code. Okay, that information is part of the DNA. That means that the amino acid composition of a protein is the same every time it's synthesized. If it wasn't, it wouldn't be that protein. So every time it's synthesized, the amino acid composition of that protein is the same. It's identical. That's the first predicate. The second predicate is that regardless of the absorbed amino acid profile, rather from, either from bacterial sources, from feeds, or from endogenous sources, or whatever, that amino acid composition of absorbed amino acids does not affect the composition of the synthesized protein. They stay the same. What it does affect is how much protein can be synthesized. The third predicate, and we'll get into this in a little more detail as we go through the presentation. The third predicate is that it's the supply of the first limiting essential amino acid that's going to determine the extent of protein synthesis, not MP. MP is very general. It's total amino acid supply. It tells us nothing about the individual amino acids that are required for protein synthesis. It's basically just telling us there's a bunch. So we're going to take a look at these three predicates and examine things a little more closely. Okay, so the first one is this idea of amino acids joined together for protein synthesis according to a predetermined code. Therefore, the amino acid composition of the protein is the same every time it's synthesized. So what are the implications of that, really? It tells us that the amino acid composition of milk proteins never varies, never. But it also tells us that the lysine-methionine ratio in milk protein is determined also by genetics, and it is constant. It never varies. That's one of the amino acid relationships that defines the protein. So what does all this mean? It means that what we feed has zero impact on the amino acid composition of milk protein, none whatsoever. It also means that what we feed has zero impact on the ratio of lysine to methionine in milk protein. So what we feed has no effect whatsoever on the amino acid composition and ratio of lysine to methionine in milk protein. Absolutely none. Let's go to the second predicate, the idea that the absorbed amino acids don't affect the composition of the synthesized proteins. What it does affect is the amount of protein that can be synthesized. Implications, again, what we feed has zero impact on the amino acid composition of milk protein. It has zero impact on the ratio of lysine to methionine in milk protein. What it does have is a major impact on how much protein can be synthesized. Okay? And that's crucial. It's significant because without appropriate lysine methionine supplies and ratios, cows are not going to fully reach their potential for milk protein yields. We'll never see what they're capable of doing because it's a metabolic and physical impossibility to build milk protein with what you don't have. Can't do it. So she won't do that. So we could sometimes be quite surprised at what cows could do in terms of protein synthesis once we give them the building blocks. This is a critical concept. It's the supply of the first limiting essential amino acid that determines the extent of protein synthesis, not MP. Specific amino acids and specific relationships to one another are required to synthesize milk protein. MP doesn't tell us anything at all about those supplies of amino acids. It simply tells us there's a bunch. That's all it tells us. The implication then is if it's amino acids that are requirements, how much MP we need is determined by the amino acid profile of MP. If the lysine methionine content, for instance, of MP is low, we're going to need more MP to get the grams of lysine and methionine that we need to increase protein yields. And conversely, if it's high, we need less MP. So MP is not really a very good indicator of what we need to do with respect to milk protein synthesis. So the implications are that even when supplies of MP lysine are better than average or high, that relationship between lysine and methionine still determines the extent of protein synthesis. It's not just the supply. It's the relationship between lysine and methionine. It's called balancing. And that relationship is expressed as the lysine-methionine ratio. So if we have decent estimates of what's being supplied in terms of MP lysine and MP methionine at the intestine, our ratio of lysine to methionine is going to tell us which amino acid of the two is limiting milk protein synthesis. And we'll get into that a little bit later. The third implication is that an appropriate lysine methionine ratio enables optimal milk protein synthesis at any level of lysine and methionine supplies. Regardless of what the supplies look like, it's the ratio of lysine to methionine that's going to determine milk protein synthesis, the extent of it. Without that ratio, optimal milk protein synthesis just doesn't happen. It's not possible. It's a physical impossibility. Okay, let's look at an example of that. In this little table, we've got 50 grams of MP methionine and graded amounts of lysine. Look at the ratio as we bump lysine up. This is the ratio of lysine and methionine in milk protein. As we bump lysine up, leaving methionine constant, we get further and further from this ideal ratio. Okay. So you can see very quickly, methionine becomes the limiting factor in milk protein synthesis. This is an important point as well. When you take a diet and you evaluate it with Formulate 2 NRC 2001, you're going to see a very different lysine-methionine ratio than you'll see in CNCPS. And in NRC, that relationship, that ratio relationship, is a very good indication of what's limiting milk protein synthesis. And it will be limiting it to yields that the MP methionine supply will support. Then in those diets, almost without exception, MP methionine is the first limiting essential amino acids. Just as a note, let me get my pointer set up here. From the same diets, Formulate 2 NRC 2001 and CNCPS do not report the same lysine-methionine ratios. They do not report the same lysine-methionine supplies. So what we're looking at here is through the perspective of NRC 2001. It cannot be applied to the CNCPS model except in very general terms. But we're going to look at a little more specific terms as we go through here. So bear that in mind. So the question becomes, these are critical amino acid balancing predicates, but what are they telling us about formulating lactating diets? We're going to examine that in 3 different areas. We're going to take a look at issues with feeds. What can we do with feeds? What can't we do with feeds? And by feeds, I mean conventional feeds, conventional energy and protein sources. We'll also look at issues with model characterizations of feeds and rumen-protected amino acids. Characterizations in terms of crude protein fractions and what actually ends up in the intestine. The final area we'll look at is issued with modeled lysine-methionine flows versus actual lysine-methionine flows. And by actual, I mean what really shows up at the intestine, because that's what cows respond to. That may or may not be in close agreement with the model values. So first we're going to look at issues with feeds, and we'll address these other 2 areas in subsequent presentations. So let's look at this. Let's look at feeds. This is a table of amino acid composition of feeds, several feeds, including protein sources, but also lean tissue from the cow, milk, and bacteria. And one thing I want to take a look at here before we get much further is you'll find that the lysine and methionine content of bacteria is very well matched with milk, the lysine and methionine content in milk protein. So from here on, we're going to focus right here. And we're going to look fundamentally at the feeds. So I've extracted them into another table there. And what we want to see is this. We've got a low lysine to methionine ratio here. Okay, and that's just, these are just the averages of all of these feeds. It's a low lysine to methionine ratio, but that's not because methionine content is high. It's because lysine content is low. Okay, and you see that when you take a look at the average methionine content in crude protein from the feeds compared to milk protein. So relative to milk protein is very low in methionine. if we were going to look for an ideal feed source, this would probably be it, fish meal. In terms of amino acid composition, lysine, methionine composition, very well matched to milk protein. Okay. However, we can only feed so much fish meal, and there are palatability issues with it and availability issues. So where most of us go, initially at least, is to blood meal, very high lysine content. But look what happens to methionine. If we're trying to increase the percentage of lysine in this little workup of feeds, the minute that we start including blood meal, we start dropping methionine. Okay, it's far below the average and very distant from the methionine content of milk protein. Let's take a look at soybean meal. On the methionine side, it's a little better than blood meal, but it's still well below the average and well below the milk protein content. So let's take a look at canola meal. That's a little better in terms of methionine on average, but it's still well below milk protein. So everywhere we look, with the exception of fish meal, everywhere we look, if we incorporate any of these feeds, any of these three, into the diet to increase the lysine content of the diet, we're dropping the methionine content. We're skewing the lysine-methionine ratio towards lysine. Now, let's just take a look at what happens if we try to go the other way and we try to improve the methionine content. Good methionine content in corn gluten meal, but what happens over here? It's a disaster on the lysine side. It's well below the average and nowhere near what we need here. Okay? So let's look at the next best one in terms of methionine content. Okay, sunflower meal, pretty decent, but look at lysine, still well below the average and far away from the lysine content of milk protein. So take a look at oats, good methionine content, slightly below average lysine content, and still miles away from where we need to be in terms of the content of milk protein. Okay. And there are issues here. We're looking at relatively low protein, mid-range at best. And there are other issues with feeding oats in terms of carbohydrates and starch content and so forth. So let's kind of summarize this, because typically what we're going to do is to use feeds with higher protein content to try to move amino acids. So we're going to look at canola meal, soybean meal, blood meal, and fish meal. Average lysine content, average methionine content, average for these feeds, 7.15. For lysine, we're getting in that direction, but look at methionine, 1.83%. That's barely above the average for all these feeds, which, you know, most of these feeds are going to end up in the diet anyway. But look at the ratio, 3.9 to 1 compared to milk protein, 2.8 to 1. So that's with fish meal included. Let's pull fish meal out. So all we're working with now is canola meal, soybean meal, and blood meal. Lysine's relatively close. But look at methionine. It takes a major hit. And look at the ratio of lysine to methionine average in these feeds. way off the mark of what we need here. Easy to see that. So what happens with conventional feeds is when we attempt to increase lysine levels, we're going to end up reducing MP, methionine content, and that's simply because of how the amino acids are structured in the protein of the feeds. By the same token, if we attempt to increase methionine levels with conventional feeds, we're going to end up reducing lysine content. So what are the implications for milk protein synthesis when we try to do all of this with conventional feeds? Simply that without appropriate lysine and methionine supplies and ratios, cows are not going to reach their full potential for milk protein synthesis. We'll never see what they're capable of doing because they never have the building blocks they need to do it. We're going to take just a couple of minutes here and look at some work that was done by the NRC 2001 committee relative to milk protein synthesis. And we're going to look at this idea that lysine and methionine are co-limiting. Okay? That's a fundamental concept of balancing diets for amino acid content to promote protein yields. In the work that the committee did, they selected, for looking at lysine content, 18 experiments with 63 treatments. When looking at methionine, they selected 27 experiments and 87 treatments. Those 45 experiments and 150 treatments met the criteria for conducting the study. These were studies where lysine and methionine were infused directly into the abomasum or the duodenum, or they were fed in protected form. But if they were fed in protected form, what was selected were diets that were restricted to the protected products that had reported viability in peer-reviewed literature. They didn't use manufacturer's specifications. They used what had been determined by the independent studies in peer-reviewed literature. And also the estimates of ruminal escape had to be 80% or higher. So that's kind of the parameters of the study. In pursuing it, 4 different statistical models were used to describe the relationship between increasing concentrations of lysine and methionine MP and milk protein content and yield response. So this was all focused on milk protein yields. So what did they find when they analyzed all of these studies? All of the models that were used indicated that low concentrations of methionine in MP limited responses to increasing concentrations of lysine in MP. So you see here a perfect illustration of this idea of lysine and methionine being co-limiting, because they also found that low concentrations of lysine in MP limited response to increasing concentrations of methionine in MP. Okay. Now, we're talking about concentrations of these amino acids in MP. But when you change the concentration of either amino acid in a given level of MP, what are you doing? You're increasing gram levels or decreasing gram levels. So this is really taking a look at gram supplies of lysine and methionine and how they interact in terms of milk protein synthesis. So fundamental point, they're co-limiting. What are the implications of that? Well, the first implication is that, optimal milk protein synthesis requires both an appropriate ratio of lysine to methionine and appropriate gram levels of each amino acid. I can get a great lysine methionine ratio with 3 grams of lysine and 1 gram of methionine. What I won't get is protein synthesis to speak of. So that's the first implication. The second implication is whether we're doing this in a research setting or on a farm trying to improve things, when we attempt to demonstrate response to an effective RP lysine product and we have an inadequate level of methionine, that's going to limit protein response. And it's going to give us a very skewed view of what's possible with effective lysine supplementation. In other words, that co-limiting relationship is going to give us a skewed view of what we can get from the lysine. And as we've seen, just as the committee reported, the same scenario is true of methionine products. If we don't have enough lysine, we're not going to see what methionine products can really do. So sometimes there's a lot of talk about the next great amino acid discovery, but I would suggest that making full use of what we already know about lysine and methionine is a prerequisite to finding that great amino acid discovery, the next one. If we don't make full use of what we know about lysine and methionine, and there's a lot of implications with making that statement, it's going to be very difficult to determine what's next. So the question becomes, are we fully utilizing what we already know about lysine and methionine? I would answer that question with a no. I would suggest that we're not. And there are many reasons why we're not, even with what we know today compared to what we knew 30, 40 years ago. So let's take a look at this idea of lysine and methionine. We know they're critical, and they have a direct correlation to milk protein synthesis. And milk protein synthesis, milk protein yields, have a significant financial impact on the producer. So it's important that we focus on these fundamentals and get a real clear picture of what's going on. Now, we've focused on feeds in this presentation. In the next segment, we'll focus on model characterization of feeds and rumen-protected amino acids and how that affects what we're able to do in terms of affecting milk protein synthesis and yields. And in the last one, we'll take a look at issues with modeled lysine and methionine flows versus actual lysine and methionine flows. And by actual, I mean what really ends up at the intestine compared to what a model might be predicting, and how that influences our efforts to formulate diets for amino acid balancing and affect milk protein synthesis. So again, what we looked at here was issues with feeds. What did we find? Well, we found that relative to milk protein, there's a significant imbalance in conventional feeds and protein sources between lysine and methionine. If conventional feeds and protein sources are all we use, we'll never see what cows can actually do in terms of milk protein synthesis. We learned that feeds are very poorly balanced in terms of ratio of lysine to methionine, whether we include fish meal or whether we don't. If we don't, we've got a much worse scenario than if we were able to. So the bottom line is that because of this imbalance, because feeds with significant lysine content are poorly balanced with their methionine content, that difference tells us that when we're only using conventional feeds and diets, MP-methionine will be the first limiting amino acid for milk protein synthesis. Okay, and that means that the higher we attempt to push lysine content with conventional feeds, the more limiting that lysine-methionine relationship becomes. So thanks for taking time to watch the presentation, and hopefully we'll see you in the following segments.